Let me start from the beginning. Okay, today we are going to cover sets, probabilities, permutations, and combinations. Okay, basic concepts of probabilities, permutations, and combinations. So the topics for today, there's 1, 2, 3, 4, 5 topics that I'm going to cover. Introduction to probabilities, basic concepts of probabilities, multiplication principle, permutations, and combinations. As I go over this PowerPoint, if the students have any questions, please just write in the chat, and then Ms. Patricia will let me know what the question was, so she can stop me. Okay, because it's crucial for you guys to have a good understanding of this week's presentation. Okay, let's start with 8.2. It's called Introduction to Probabilities. Random experiment. Okay, what's a random experiment? It's a process by which we observe something uncertain. After the experiment, the result of the random experiment is known. The sample space is denoted by S. It's a set of all possible outcomes of the random experiment. For example, say that you flip a coin twice. Just flip a coin once. What's the sample space? The sample space, it can either be heads or it can be tails. So the sample space is heads. S equals to the with a bracket, right? Heads, H, comma T. H for heads and T for tails. Same thing for rolling a third die. A third die means that the die is all the sides weigh the same, because at times the dice might be loaded. Okay, that's why it says a third die, which means every single number has an equal chance to be rolled. So, for example, the sample space of a die to be rolled can be a 1, a 2, a 3, a 4, or 5 over 6. So this is my sample space. Okay, now to find the sample space of an experiment, at times it is easier to draw a tree diagram. For example, find the sample space of flipping a coin twice. Okay, so flipping a coin twice. So this is my first flip. It can be heads or it can be tails. Right, this is my first flip. Now my second flip, it can be heads. It can be head. The first row can be the first toss can be a head, and then it can be another heads, or it can be a heads and it can be a tails. So this is my second flip. And then if the coin was tails first, right, then it could be tails heads and tails tails. So this is my sample space. It's going to be heads heads. It's going to be heads tails. It's going to be tails heads. And finally, tails tails. So this is considered my sample space. And you have to put it with a brackets. So it can be HH, right, for heads heads, HT for heads tails, TH for tails heads, and TT for tails tails. So like I said, at times it's easier to draw a tree diagram to find your sample space. Okay, now an event. An event is an outcome or a set of outcomes of a random experiment. For example, an event is a subset of a sample space. If the sample space for flipping a coin is heads tails, then one event is the event E, right? For it to be heads, so this is the event, which represents the outcome heads. Checkpoint. Suppose a die is tossed. Write the given events in said notation. For A, the number showing is less than 3. So before we do that, the solution, right, for the sample space, it can be a 1, 2, 3, 4, 5, 6, right? Because a die has 6 sides. So for the number showing is less than 3, it can be 1, right? Because 1 is less than 3, or it can be 2 because 2 is less than 3. So this is the result for A. It can be 1 or it can be 2. That's the event for the number showing is less than 3. Now B, the number showing is a 5, right? So there's only one way we can get a 5. So that's the answer right there. See, the number showing is an 8. Okay, do we have an 8 here? No, right? So this is going to be an empty set. That's a notation for an empty set, or the set of brackets with nothing in there. The number is an even number. Okay, so it can be a 2, a 4, or a 6. So this is my event. Okay. Okay, now comes the basic probability principle. So if you let S be a sample space of equally likely outcomes, and then event E be the subset of S, then the probability that event E occurs is the probability of E equals to the number of the event over the number in the sample space. The instance is going to be a number. Okay, but this definition, the probability of an event is a number that indicates the relative likelihood of the event, right? So it's going to be a number. N of E is the number of elements in the event, and N of S is the number of elements in the sample space. Everything that I put in red, guys, is very important. Okay? Checkpoint. Suppose a single die is rolled with a sample space. The sample space will be 1, 2, 3, 4, 5, 6. Give the probability of each of the following events. The die shows an even number. Okay, so that shows an even number, so it's going to be, so even number, right? This is the event. It can be a 2, a 4, or a 6. So there's going to be 3 elements. So N of E is 3, right? And my sample space will, will always be 6 if one die is rolled. For example, this is my sample space, right? My sample space, it has 1, 2, 3, 4, 5, 6 elements. So by using the definition, the probability of the event that the number is even is going to be 3 over 6, which then you reduce it, the same thing as 1 over 2, which is 1/2. Now let's try B. The die shows a number less than 10. Right, so less than 10, the event is going to be all the possible numbers, right? Because all these are less than 10. So then the N of E is going to be 6. The sample space is 6. So the probability of this event is 6 over 6, which will be 1, or like 100% that this is going to happen, right? The die shows an 8. Right, none. There's no elements, 0 elements that are 8, because it's only 1 through 6. So N of E is 0, and N of S is the same as before, which is 6. So the probability will be 0 over 6, which is equal to 0. So there's no way it's going to happen. That's what that means. Okay, now this one, a single playing card is drawn at random from an ordinary 52 card deck. Find the probability of drawing a queen, a diamond, a red card, a face card, or an ace. Here, guys, I give you a copy, or I show you what the cards are, because nowadays I believe students or kids nowadays, they don't play cards. They like to play video games and stuff. But when I was growing up, we used to play all sorts of card games. That's why I decided to show visually how the cards look like, just in case you never seen these cards or you don't play cards. Okay, for example, there's really 54 cards in a deck of cards, because there's 52 cards plus 2 jokers. Okay, just in case you didn't know. But here, they're not considering the jokers. Okay, there's going to be 13, these are called clovers or clubs. There's 13 clubs, and they go from the ace, right? The ace is like 1, or it can be the ace can be a 1, or it can be the highest number over here. After the king, right? But for now, the ace is like a 1. Then you have a 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then you have a jack, a queen, and a king. If you notice, there's going to be 13 cards of each, like 13 clovers, 13 spades, 13 hearts, and 13 diamonds, right? 13 clubs, 13 spades, 13 hearts, and 13 diamonds. That's where the 52 total cards come from, right? Because if we add all 13 plus 13 plus 13 plus 13 will give us 52. That's where it comes from. Okay, now if you notice, These are called suits, okay? The clubs is called a suit. The suit of clubs, the suit of spades, and so forth. So there's 13 cards for each suit. If you notice, there's 13 black. I mean, there's 26 black and 26 red. Okay. Now, there's 3 face cards for each suit. What are face cards? Face cards are the cards that have a face on them. Like, for example, the jack, the queen, and the king, they're going to have a face. You see, this is a jack, queen, king. That's why these are called face cards. If you notice, there's 3 face cards for each suit. So there's three. I mean, there's going to be 4 kings, 4 queens, and 4 jacks because there's 4 suits. So there's total of, right, for the queens, right? There's total of 4 queens because there's 1 for each suit. So to do A, the probability for it to be a queen, we know that the sample space is 52, right? Because there's 52 total. That's my sample space. So the queen is going to be 4, right? Because there's 4 queens. Like I said, there's a queen of diamonds, queen of hearts, queen of spades, and queen of clubs. So there's four queens. So it'll be over the sample space, which is 52. So 4 over 52 is going to reduce to 1 over 13. So this is my final answer. Okay. Now let's do B. The probability of a diamond, right? So we know there's 13 diamonds, right? Because it's obvious, or you can see that they're here for 13 diamonds. So for the probability for it to be a diamond, right? There's 13 diamonds, and over the sample space, which is 52 again. 13 over 52 is going to be 1/4. So this is the final answer because you have to reduce. Okay, now a red card. So there's 13 hearts and 13 diamonds, right, which are red. So there's 26 total red cards over the sample space. So it'll be 26 over 52. The answer will be 1/2. Okay. Now finally, a face card or an ace. Here, guys, they're asking for a face card or an ace. Okay, so how do we do D? So how many face cards do we have, right? We have 12 face cards, right? Because there's 3 of each suit, and 3 times 4 is 12. And also there's also four aces, right? There's an ace of clubs, an ace of spades, an ace of hearts, and an ace of diamonds. So it's going to be +4 over the sample space, which is 52. So 12 plus 4 is 16. 16 over 52 is going to be something like 4 over 13 if you round out. I mean, if you reduce. Okay. So these is how you do these type of problems. And I believe for the homework or the book or my math lab, there's a whole bunch of probabilities relating to cards. Okay, so this can give you an idea how to work them out. Okay, now this is 8.3. This is basic concept of probability. This example, right, it says to use the addition rule for probabilities. For any event E and F from a sample space S, the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersects F. So we're going to be using this formula here. Okay. Okay, now this is example number 1, and I believe there's also homework problems relating to this roulette table. Example 1 says, when playing American roulette, the cropper, who is the attendant, spins a marble that lands in one of 38 slots in a revolving turntable. The slots are numbered 1 through 36, with 2 additional slots labeled 0, 0 and 0, 0 that are painted green. That's supposed to be enough, right? But I put an or, it's supposed to be an S there. Half of the remaining slots are colored red and half are black. In roulette, the slots labeled 0 or 0, 0 are not considered as even or odd. Okay, now here's what you want to find. Find the probability that the marble will land on a red or even. So let's diagnose this problem here. Okay, solution. Let's say of red BR, right? So we're going to R represents the set of red, right? These are all the red guys. I went all around the roulette table and I put all the red the red numbers or the red slots. You see, you notice there's my 1, which is red. There's 3, right? And if you go and put all the red slots, they're all listed here. Okay, I already did that for you guys. Okay, now the set of even BE, right? So E is equal to, these are all the even numbers from 1 through 36. Because remember, guys, even though there's 38 slots, the 0, which is here on the bottom at 6 o'clock, and the 0 here at 12 o'clock, these two are considered not even or odd. Okay, so there's 38 total. Okay, now, so here's my formula. Okay, the probability of R union E equals to the probability of R plus the probability of E minus R intersects E. Hey guys, this right here means what they have in common. Okay, so how many are how many are red? There's half, right? So half are red is going to be 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's total of 38. There's 18 black. There's 18 red. There's 18 black. There's 18 even and 18 odds. You see, I just counted them for you guys, but here is it's what they are. So the probability of red. Okay, so we're looking for red and even. Okay, red and even are going to be 8, right? Because red and even are here, right? These are red and they're even. There's 1, which is a 12, 14, 16, 18, 30, 32, 34, 36. So there's 8 that are red and even. That's why it's 8. So the probability of red intersects even is going to be 8. Okay, so let's put everything down here. So the probability of the event is equal to the number of E over the number of S. Okay. So that's why it's going to be, there's 18, right? 18 red, we put them over 38 because there's 38 total. Plus, there's 18 even, so it's going to be 18 over 38, which will take care of the even. Minus the probability of red intersects even, right? Red and even is going to be 8 over 38. So then, right, so then 18 plus 8, or what's 18 minus 8? Wouldn't it be 10? And 10 plus 18 will give us 28. So this is my result. And all we do is simplify. So that's your final answer. Hey guys, for most of these problems, at times, they might seem a little bit challenging, but if you put all the information, put it on your paper, and then the problem will not be that complicated. Okay, because at times, when students see something like this, right away, it's like a turnoff because it seems kind of hard. But like I mentioned earlier, just break down the problem into everything that it's asking for, and then just fill in the addition rule of probability, which is this formula here. You just fill in what they want, and then you get the result. Okay. This is example 2. Suppose 2 fair dice are rolled. Find each of the given probabilities. The first die shows a 2, or the sum of the result is 6 or 7. And for B, the sum is 11, or the second die shows a 5. Okay, I'm going to show you, right? So for part A, we can use this formula here. Let A represent that the first die shows a 2, right? So A represents the first die is a 2. And let B represent the event that the sum is 6 or 7. Okay, so it's always wise to have some kind of all the possible combinations when you roll 2 dice. Okay, so these are all the possible combinations. If you notice, this is event A in red. Why? Because event A says that the first die is a 2, right? So this is a 2. You see the first die is a 2. But the sample space, guys, will always be 36 when you roll 2 dice, because there's 1, 2, 3, 4, 5, 6. There's 6 across and 6 down, so 6 times 6 is 36. That's my sample space. So for the event A, it's going to be what? It's going to be 6. There's 1, 2, 3, 4, 5, 6. And then for event B, right? It's going to be 11, right? Because these are equal to 6 or 7, right? If you go all the way across like this, guys, all across. Let me show you again. Across, there's these are the 6s and these are the 7s here. The sum of 7. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's where that comes from. Now, where do these two intersect, right? So they intersect right here, guys. Right, so this is the event A plus event B minus, where do they intersect, right? So we're looking for this one here. They intersect here and here. So there's 2. So it's going to be 2 over 36. So then 6 plus 11 minus 2 is going to give us 15. 15 over 36. And then all we do is simplify. So the answer is 5/12. Okay. Now, let's do B again. So for part B, the sum is 11, or the second die shows a 5. So I believe we're going to, there's my table again with all the possible combinations. So again, the sample space will be 36. Again, we're going to use the same formula. So we're going to let A represent the event that the sum is 11. So the sum is 11 is going to be A, the event A. Right, so for the event A, right, I mean, the sum to be 11, it can only be a 5, 6 or 6, 5. So there's only going to be 2. Okay. Now, let B represent the event that the second die shows a 5. So this is my first die, right? So my second die is here. So my second die is a 5. It's going to be this one here. You see the second die is a 5. It's going to be 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, and 6, 5. So it's going to be all those. So how many are there? 1, 2, 3, 4, 5, 6. Right? And then where do they intersect, right? They intersect right there. So it's going to be 1. Okay, so now just go back and use the formula. So it's going to be 2 over 36, right? Because that's even A, plus 6 over 36 minus 1 over 36. 2 plus 6 is 8, minus 1 will give us 7. So this is the answer, 7 over 36. That's how you do these type of problems. And like I mentioned earlier, guys, with the cards, there's a whole bunch of different problems, guys, that are there in the homework and also on my math lab. I just went over a few so you guys can have a basic idea how to work them out. Okay, now this is called the complement rule. It says for any event E, the complement means not E. Okay, so the probability of the complement E is equal to 1 minus the probability of E. And vice versa, the probability of E is equal to 1 minus the complement of the event E. Now here comes odds in favor, the odds. The odds in favor of an event E are defined as a ratio of the probability of E to the probability of not E, or the probability of E over the probability of not E. And the probability of not E cannot be 0 because if it's 0, it'll be undefined. Okay, observation, okay? That's why this is where the formula comes from. Right? The probability of E or the probability of not E, right? This is the probability of E, the number of the event over the sample space. And the probability of not E or the complement of E is the number of complement of E over the sample space. If you use basic algebra, right? So N of E over N of S, right? Divided by the number of complement of E over the sample space, right? So this division becomes multiplication. And the second fraction, you flip it. So the N of S goes as your numerator, and the number of the complement of E goes in the denominator. So here, right, these cancel to 1. So you're left with a formula right there. Okay, that's why this is your formula. Okay, now, this is number 27 from the book, page 434. It says a marble is drawn from a box containing 3 yellow, 4 white, and 8 blue. Find the odds in favor in drawing a yellow marble, a blue marble, and a white marble. Okay. Solution. right? So we're gonna add all the marbles, right? Because that's my sample space. So we're gonna, we're gonna add them all. Oh no, guys, if there's a probability, we're gonna add them all, right? Because we need the sample space here. Here, guys, for the odds in favor, we don't need the sample space. The odds in favor and drawing a yellow, okay, is the I call it the easy version, okay? How do I understand these right here? It's going to be yellow. That's what it means by the event, right? Or not yellow. That's why I put, right? The event is yellow, right? And this is the not yellow, or the complement of yellow is not yellow. So to make it short and sweet, this is how you're going to get your answer, guys. Whatever they want over the rest. So how many are yellow? It's going to be 3. How many are not yellow? It's the white and the blue, which is 4 and 8. We add them up. 3 over 12, which will be 1/4. But the answer should be in this form. 1, 2, 4. That's what that means. Okay? That's the odds in favor. Okay, now that means that 1, right? The probability, the chance of 1, the 1 in favor and 4 not in favor. That's what this really means. Odds in favor drawing a blue, right? So it's going to be blue over not blue. So how many are blue? There's 8 blue. How many are not blue? Are the yellow and the white, which is 3 and 4. So we add the 3 and 4, so it's 8 to 7, which means the chances for it to be a blue out of the situation is 8 to 7. 8 in favor and 7 not in favor. Okay. Now see, odds in favor and drawing a white marble. So again, white over not white. So there's going to be 4 white, and the not white are the yellow and blue, which are 3 plus 8, which would be 4 over 11, which would be 4 to 11. So this is your result. Okay. Because I remember when I was taking this course that this seemed kind of hard for me, but as I do the notes and as I do go over the material, I just found this is much easier for students to understand. Okay. So that's what I use. First I show them the concept, which I did here, and then I show them like observations by doing this right here, like the yellow and not yellow. Okay, now this is exercise 47 to 54 on page 435. Okay, this is the data from the 2016 General Social Survey can allow us to estimate how many hours people who classify their work status as part-time, full-time actually work in last week. Use the following table to find the probabilities of the events. Okay. So for 47, right? So it's going to be the probability of the event, which will be the number of the event over the sample space. If you notice, guys, this is my sample space, right? That's my total, right? And the event, for example, that's going to be my sample space for all of these problems here, because you're looking for the probability. Okay, now full-time workers. So hey, guys, where are my full-time workers, right? So it's going to be this right here, right? So it's going to be, these are all my full-time workers. So what's the total? 1271. So the probability of a full-time worker out of the sample space will be 1271 over 5091. And I believe they're gonna want you to round off to 4 places. So you put this in the calculator, guys, it should give you something like approximately 0.7989, round off to 4 places. Now, number 48, a part-time worker, right? So part-time worker is 320, right? These are my part-time workers. So we go here, at the total will be 320. So 320 over the sample space, which is 1591. And again, you put it in the calculator, guys, and it's approximately 0.2011 is a probability. Number 49, work 50 hours or more. So again, we know that the sample space is the same, right? 1591 throughout. Let's go here, 50 hours or more. So it's going to be 50 hours or more. It's here, right? So we go all the way down. So it's going to be 393 over my sample space, which is 1591. Use the calculator, and approximately it will be 0.2470. Number 50, work 0 to 19 hours, right? So 0 to 19 hours is going to be right here, right? So we look here at the chart, 0 to 19 hours, so we go all the way down, it's going to be 106. So the probability will be 106 over the sample space, which is 1591. And again, put it into the calculator and round off to 4 places. So this is what it should round off to, 0.0666. Okay. Okay, now 51 through 54 are a little bit more challenging because you have the and you have the or. Okay, so let's do 51. Okay. So again, the same thing before, right? So this is from before, right? From the previous slide. So the sample space will always be 1591. So it says here, guys, part-time worker and someone who worked 40 hours. So we go here to part-time worker and someone who worked 40 hours or more is going to be these two right here, guys, right? These two work 40 hours or more, right? That's what it means. So that's why it's going to be it's going to be it's going to be this one here, part-time workers. It's going to be 49, right? Because these two work 40 hours or more. That's why it's 49 plus 21, which will give us 70 over 1591. It's going to be 0.0440. Let's do 54 now. Part-time worker or someone who worked 29 hours or less, right? So this is the main thing is or. So for or, guys, right, we're going to use the formula from before, the addition formula. So P of E, okay, let me show you where this came from, okay? So part-time worker, right? So for part-time worker, we're going to go all the way over here on the part-time worker. So it's going to be 320, right? And then someone who worked 29 hours or less. So then we go here. Let me see, part-time worker or someone who worked 29 hours or less. So 29 hours or less, wouldn't it be these two here, right? Because you see these are 29 hours or less. From these two are considered 29 hours or less. So we go here to the total, right? That's why it's going to be 129 plus 106. And then minus, this minus means because these right here, they already counted before. They were counted over here with a 320. That's why we subtract 77 minus 87. Okay, so this is how we do by using this formula, guys, just in case you did not understand this part over here on the left. So let A represent the part-time workers, right, which will be 320. And let B represent 29 hours or less. Okay, so we got 320, right, because the part-time workers are 320, right, 320. The ones that work 29 hours is going to be these two here, right? This is considered 29 hours or less, which is a 106. And this is considered also 29 hours or less, which is 129. That's why we have these two, which is 106 plus 129. Minus, right? This is where they intersect or where they have in common, right? So they have in common these two here. That's why it's 77 plus 87, and we subtract those. So your answer should be 391 over the sample space. Rounded off to 4 places, so it's going to be 0.2458. I believe 54 is like the hardest one for students to do. But if you use a formula, guys, it makes more sense. Okay? Okay, now, this is called the multiplication principle. Permutations and combinations. This is section 9.2. So the multiplication principle say that suppose n choices must be made with m1 ways to make choice 1, m2 ways to make choice 2, and so forth. So we just multiply the possible ways. Example, this is number 24 from page 477. It says how many different heating cooling units are possible if a homeowner has 3 choices of the efficiency ratings of the furnace, 3 options for the fan speed, and 6 options for the air condenser. So we're going to multiply all those options, right? So here we go. Solution, use the multiplication principle. You see these are the number of choices for efficiency ratings of furnace, right? Which is the first one, which is going to be 3. The number of choices for the fan speed, which is going to be also 3. And the number of choices for the air condensers, which will be 6, right? So this will be 3, that'll be 3, and that'll be 6. So by using the multiplication principle, it's going to be 3 times 3 times 6. The answer is 54. So 54 different ways that this can be arranged. Okay. So let's do another one here. This is number 28 from page 477. The United States Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are not restrictions on the digits used? That's for the first part. For the second part, how many would be possible if the first number could not be a 0? Okay, so let's find out. I tell my students to actually, if you have 5 digits, right? So these are the digits that make all the numbers, or the possible digits for each one. So I like to do it this way, right? I'm going to put a blank, 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 right? Because there's 5 digits. 1, 2, 3, 4, 5. So we put blanks. Okay, for the first one, right? There's no restrictions. How many zip codes are possible if there are not restrictions on the digits, right? So how many digits can go here? All these can go there. So there's 10, right? So it's going to be 10. I mean, those are my 5-digit zip code. 10 can go there, and there, on the 3rd slot, on the 4th slot, and on the 5th slot, right? Because there's no restrictions. So the answer will be 100,000 possible ways. Okay, now for the second part, which is how many would be possible if the first number could not be a 0. Right? There, let me go back real quick. Why is this 9 in the first slot, right? There's only 9 digits because the first number cannot be a 0. That's why there's only 9. And then we got 10 and 10 and 10 and 10 again. You multiply it out, the answer will be 90,000. I believe in some of the homeworks, they're also talking about license plates and stuff like that. Well, I mean, here they are, here, number 30. Number 30 from page 47 says, for many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. Okay? So no 26 letters on the alphabet and 10 digits make all the numbers. How many different plates are possible with this arrangement? Okay? So, right, so these are my letters and these are my digits. And here, guys, they don't say nothing about, right, a restriction. So this will be 26, right? So this will be 26 letters times 26 times 26 and 10, 10, and 10. If you multiply that out, it's going to give you like 17,576,000 possible ways. Okay. Now for B, when the state ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. How many new license plates were then possible? Let's do that. So here they reverse the order. So these are the digits and these are the numbers. Again, there's no other restrictions, just what they just mentioned that they switched them. So 10 digits can go there and also on the 3rd slot. And for the letters, the same thing, right? 26 can be the first letter, 26 can be the second letter, and 26 can be the 3rd letter. If you multiply them out, you get the same answer as part A, which is 17,576,000. Okay, now let's go to C. Several years ago, the number described in part B were also used up. The state then issued plates with 1 letter followed by 3 digits and 3 letters. How many new license plates will this arrangement provide? Hey students, check this out. Just by adding one more letter to part B, look at how many, look at the difference that it's going to make, right? So this is about 17.5 million. Now let's see what happens when we add 1 letter extra. There's my letter extra, right? Those are my digits, and these are the last 3 letters. So 26 letters can go there, right? And besides this arrangement, there's no restrictions. So it's going to be 10, 10, 10, because 10 digits can go here. Also 26 letters, and 26. If you multiply them out, this is the answer. Imagine, guys, with only one letter that they added, they go from 17 million, 17.5 million to almost 457 million. So that letter made a big difference. Okay. And I believe, guys, that's the way the license plates were made at the beginning, when cars were recently, were just built. At the beginning, there was only a few cars, right? A few cars at the beginning, like in the 1920s, 1930s. So then they just keep putting like different license plates, right? Like different numbers, but probably back then they only used like 2 letters or 2 numbers or something like that. Then as more cars were made for each state, then they began to add letters and digits to the plates. I believe nowadays, I think there's like my car has 3 letters, I think 3 letters and 4 numbers. Here for the state of Texas. So that's how they keep adding numbers and stuff, and numbers or letters, guys, to make more plates, because all plates have to be different for each state. Okay, let me continue. Okay, now this is n factorial. N factorial, right? This is a symbol for n factorial. It means that you begin subtracting 1 every time. So it's going to be like n times n minus 1 times n minus 2 times ... and then you get 3, 2, 1. And by definition, 0 factorial is equal to 1. Okay. So for example, checkpoint. Evaluate a, which is 4 factorial. It's going to be the same thing as 4 times 3 times 2 times 1. You multiply it out, right? So 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 24. Also, this can be put in the calculator. Okay. I believe if you have a graphing calculator that you rent out to college, I believe you're going to put the number 4, then you're going to go to math, and then you're going to go to probability, to PRB, and then you go down to factorial to where the symbol is, and then enter it, and it's going to give you that answer. Okay, but it's always good to know how to do it by hand. 6 factorial will be the same thing as 6 times 5 times 4 times 3 times 2 times 1. You multiply it out, that's your answer. 1 factorial will just be 1. Okay. How about D? 6 factorial divided by 4 factorial. So 6 factorial is the same thing as 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is the same thing as 4 times 3 times 2 times 1. If I wanted to, guys, I could have stopped here. I would have put 6 times 5 times 4 factorial and cancel the 4 factorials, and the answer would have been 6 times 5. But here, guys, right here, I'm showing you guys like the long way, right? What takes place. So here, guys, the ones cancel to 1, the 2s, right? They cancel to 1. Same thing with the 3s. Same thing with the 4. So all these is the same thing as 1 times 1 times 1 times 1 4 times 6 times 5. The answer will be 30. So that's the answer for 6 factorial divided by 4 factorial. Okay, now these are called permutations. A permutation of set of elements is an ordering of the elements. For instance, there are 6 permutations ordering of the letters A, B, and C, right? There's 6 permutations. These are all the possible orders. Okay, now the order matters. For example, A, B, C, and C, B, A are 2 different orders. How many? Okay, now this is an example. Okay, here, guys, for permutation, the order matters. How many batting orders are possible for a 9-person baseball team? So what would it be? Right, there are 9 possible choices for the first batter. So this, I do it this way, guys. Right. So these are the batters 1 through 9. Because if you put 9 factorial, that's going to be your answer, guys. Okay, it's going to be 9 factorial. So the answer for 9 factorial will be 362,880. Right, same thing as 9 factorial. Because on the first lot, 9 batters can go there, and then on the second slot, 8 batters because the batter that batted first cannot bat again. That's why it's 9 times 8 times 7 times 6 and so forth. And again, same thing as 9 factorial. So these are the same answers. 2 ways to get the answer. Okay, now these are called permutations. Permutations, the order matters. Okay. For example, I have three letters, A, B, and C. I would like to know how many two-letter arrangements are possible. Right here, the order matters. For example, A, B, and BA are two different orders because the order matters. So it can be AB, it can be BA, it can be AC, CA, BC, and CB, right? So the answer is 6. 6 possible arrangements. Okay, now how do we find it? By using the formula. Okay, so we're going to put 3 permutation 2, right? Because 3 is a number of letters and we want them in twos. That's what the R stands for. Right, so 3 factorial over 3 minus 2 factorial. So here the answer will be 3 factorial over 1 factorial because 3 minus 2 is 1 factorial. So 3 factorial is the same thing as 3 times 2 times 1 over 1. The answer is 6, right? That's what it means by here. I like to use the example, guys, for permutation and combinations because making 3 letters and pairs of 2 is easy to explain. But then once you have more letters, guys, right, it's hard to explain it, all the different arrangements. That's why I like to use this example here. Or, guys, this can be or, right? Or it can be you have 3 letters, right, and 1 arrangement of 2. So you're going to put 1, 2. How many can go here? Of the A, B, and C, isn't it 3 letters? Because A can go there, B can go there, and C can go there. And then times. If you already chose a letter, right, say you chose letter C here, how many are left? 2. So the answer will be 3 times 2. Only the permutations can be done in 2 ways. Okay? This is number 40 on page 478. From a cooler with 8 cans of different kinds of soda, 3 are selected for 3 people. And how many ways can this be done? Okay? So it's going to be 8 permutation 3. Why? Because there's 8 different kinds of soda, and and 3 are selected for 3 people. So what's the answer, right? It's factorial over 5 factorial. You see here I stopped that I told you earlier, guys, right? When it was 6 factorial divided by 4 factorial, I did it along with the other way, but here, right, we stopped at 5 factorial because here, guys, they're going to cancel right here. That cancels to 1. So we're there with 8 times 7 times 6, which will give us 336. Now, what's the other way we can do it, right? We can also do it this way, right? By putting 3 blanks there. Or you have 8 cans and 1 arrange 3, right? So it's going to be 1, 2, 3. So if there's 8 different kinds of soda, right? How many can go here, right? On the first selection, right? It can be 8. Once you pick one of the 8, right? You cannot pick it again. That's why there's going to be 7 left. And after you pick the second type, there's going to be 6 left. You see, you multiply it out, and we get the same thing as here on top, guys, of the permutation. That's why here, guys, you can do these 2 ways. The answer is 336. Now, combination, guys. The combination here is the order does not matter. Okay, for example, A, B, and BA is the same thing. Okay, going back to the example that I used for permutations. Right, I have 3 letters and I want to use them in groups of 2. Again, the order does not matter. It can be AB, it can be AC, and it can be BC. Those are the only ways it can be because if we put BA is the same thing, right? So that way here, the order does not matter. So AB and BA is the same thing. So the answer is 3. How do we do it? By using the formula for combination. It's going to be 3 combination 2. So by using the formula, right? This will be 3 combination 2, so it's going to be 3 factorial over 2 factorial times 3 minus 2 factorial, which will give you 3 factorial over 2 factorial times 1 factorial. So 3 factorial is the same thing as 3 times 2 times 1. 2 factorial is the same thing as 2 times 1. And 1 factorial is the same thing as 1, right? So 2 cancels, 1 cancels, so we're there with 3 over 1, which is 3. That's your answer. Okay, now, this is number 46 on page 478. There's 4 items are to be randomly selected from the first 25 items on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? Right? So here, guys, it doesn't matter the order, right? Because what they're doing here, they're going to select 25 items, right, to determine the order of a defect rate. And then they wanna get how many different samples of four items to be chosen at a time. So it's gonna be 25 combination 4, right? So there's how you do the work, right? So this is how you do it by hand, but this can be put in the calculator, guys, to get the answer. But here, guys, 25 factorial will be the same thing as 25 times 24 times 23 times 22 times 21 factorial. Why did I stop here? Because this is 21 factorial. That's why these will cancel here. But I have to do the factorial for 4. 4 times 3 times 2 times 1. 3, guys, those cancel to 1. What's 4 times 3 is 12. 12 times 2 is 24. So these cancel with the 24. So the answer will be 25 times 23 times 22. That's your result. Or you can go straight, if you plug this in the calculator, you can go straight to the answer. Okay? Okay, now these are key words. Okay, this is a formula for permutations, and this is a formula for combinations. So these are the key words for permutations: arrangement, schedule, order, and order matters. And the two words for combinations will be group, committee, set example, order does not matter. Okay? So now, this is, I believe we have like 3 more examples here, and I believe it's already almost time, and we have about 5 minutes, right? Something like that. I think we are going to finish on time. Because also, guys, I tell my students that that it's real hard to win the lotto. Okay, this is only like an example. This is number 59 from page 478. It says a lottery game requires that you pick six different numbers from 1 to 99. If you pick all 6 winning numbers, you win $4 million. How many ways are there to choose 6 number if order is not important? So what we're going to do here for A, right, the order is not important, but it's going to be combination, right? So it's going to be, right, there's 99, so it's going to be 99 combination 6. So that's the answer. I just plug this in the calculator. So that's the answer right there. I believe it's 1,120,529,256. Right. So imagine, guys, for you guys to win the lotto, wouldn't it be 1 over that? So those are the odds against you that I mean, for you to win. That's why it's really impossible. Because for one winner, right, for you to be the winner, it's going to be 1 over all that right there, which is 1 billion and something, guys. Now for part B, for part B, the order matters, right? So for part B, it's going to be a permutation. So that's your formula. This is going to be a lot more than part A. See, guys, it's 806,781,064,320. Okay. Okay, now number 60. It says here, in exercise 59, if you pick 5 out of 6 numbers correctly, you win 5,000. In how many ways can you pick exactly 5 numbers of the 5 of the 6 winning numbers without regards to order, right? So it's going to be a combination. Okay. Okay, now. So, right, so to win 5 out of 6 numbers correctly. So 5 out of 6 winning numbers, when it be 6 combination 5, right? To get the 5 numbers out of 6. And then it's going to be times, right? But remember, lottery requires for you to pick 6 numbers from 99. So then it's going to be, right, because there's, I mean, for the 6 numbers, right, if you got these 5 right, there's still 1 left. And if you got those right, the 6, there's 93 left. So it's going to be times 93 combination 1. Because there's a good way to understand these. The first 2 numbers in the combinations must equal to 99. You see right here. Same thing what I'm doing here, guys. Right, which are those right there. And these must equal 6, right? Which is the second number of the combination. Right? That's why, because there's 99 numbers and you have to choose 6. So if you multiply that out, it's going to give you 6 times 93, which is 158. Okay. Okay, now, I think this is the last one here. Number 58 from page 479. A financial advisor offers 8 mutual funds in high risk category, 7 in the moderate risk category, and 10 in the low risk category. An investor decides to invest 3 high risk funds, 4 moderate risk funds, and 3 low risk funds. How many ways can the investor do this? Okay, so here we're going to be using combinations. Okay, order is not right, so order does not matter, so we're going to be using combinations. So we have 8 mutual funds, and we're going to invest, let me see here, 8 mutual funds in high risk, so we're going to invest, right, so here with the high risk will be 3. So it's going to be 8, invest 3 from the 8 is going to be 8 combination 3. And then for the moderate risk, right, we have 7, and we're going to invest in 4, right, so 4, so this will be invest 4 from the 7 in moderate risk, so it's going to be 7 combination 4. And finally, right, we have the low risk, which are 10, and we want to invest 3. So invest 3 from the 10 in low risk, so it's going to be 10 combination 3. So 8 combination 3 will be 56. 7 combination 4 will give us 35. And 10 combination 3 will give us 120. And this, guys, like I said, you can put this in the calculator because it'll be much easier in the calculator. So now you're going to multiply 56 times 35 times 120. So that's your answer, guys, 235,200. So that's the number of ways that this investor can do this situation here. So 235 ways to select the funds. Okay, guys, I believe I gave you like enough for each section that you guys can follow it and be able to do the homework. Okay, guys, is there any questions? Okay, guys, so now let me go back to the main screen here. So let me stop sharing here. Okay, now guys, is there any questions with what I just covered? Marcia, you okay? And Velia?
No questions, Mr. Azasi. I think Raphael's going to wrap it up.
Okay, thank you. Thank you.
Alrighty. Thank you so much to Mr. Asasi for presenting today. Thank you to the audience for coming and being a wonderful audience. We did cover some great material, so I hope everyone learned. We hope your spring semester has been going by well. We are almost done, approximately 2 more weeks. And I would like to invite you guys to next week's TVE events. At 1 p.m. we'll have Reduce Anxiety with EPCC Mental Health Committee at 1 p.m. And then at 3 p.m. we'll be having our final Happy Math Hour event, which will be a final exam review. So I hope everybody can make it so we can prepare for those finals and get those good grades. So I hope to see you next week, and I hope your semester is finishing strong.